For centuries, human observation of the animal kingdom relied on what we could see from the outside. We mapped territories, categorized behaviors, and concluded that non-human life operated primarily on reflex. The sounds echoing through forests and oceans were largely categorized as simple, reactive signals, fixed biological responses to hunger, mating, or fear. When scientists first deployed environmental microphones into the wild, they expected to easily isolate and categorize these sounds. They dropped hydrophones into ocean currents and strapped recorders to tree trunks, capturing the raw audio of the natural world. But nature is hypervocal. A grid of just 50 sensors in the Congo Basin generates 7 terabytes of audio every 3 months, the data equivalent of 2 million songs. Human researchers were quickly overwhelmed, spending months or even years manually scrubbing through static and ambient noise to find a single relevant animal call. We had successfully built the physical hardware to record the planet. What we lacked was the computational capacity to process that sheer volume of data and actually comprehend its underlying structure. That computational deficit has recently collapsed. Researchers are now routing millions of hours of raw, unlabeled environmental audio through self-supervised foundation models like NatureLM-audio. These AI systems don't need humans to label the sounds. They ingest raw audio waves and translate them into mathematical coordinates. By plotting these coordinates, the model autonomously discovers recurring acoustic structures that human ears miss. Off the coast of Dominica, this approach is being applied to sperm whales. For decades, researchers knew these marine mammals communicated using rapid, rhythmic sequences of clicks, known as codas. By running tens of thousands of these codas through machine learning algorithms, scientists discovered that the clicks are not random. They contain highly structured properties, elements analogous to human vowels and diphthongs, combining to form a distinct phonetic alphabet. These models reveal that the natural world possesses deep internal logic. The data confirms highly organized communication, placing science at the threshold of decoding interspecies language. This pattern recognition scales directly from individual communication to the mapping of entire ecosystems. In the dense African rainforest, tracking animal populations requires filtering massive scale through chaotic noise. African forest elephants are considered critically endangered, yet visually tracking them from the air is blocked by heavy jungle canopy, and ground patrols are restricted by the harsh terrain. This spectrogram displays how deep neural networks process the environment. The system scans chaotic background frequencies to isolate the low-frequency rumbles of forest elephants. By migrating to cloud infrastructure, a backlog that once took biologists months to decode is now processed in 22 days. Eliminating that processing delay changes the nature of ecological research. Conservationists are no longer auditing historical records of where animals used to be. They are tracking active, living populations in near real time. Higher up in the forest canopy, this exact same AI technology is mapping smaller-scale social intelligence. In northern Spain, ecologists are studying the cooperative breeding carrion crow. Because standard environmental microphones miss quiet interactions, researchers attached miniature biologgers directly to wild crows. These tiny devices capture the subtle, close-range vocalizations the birds share throughout the day. The volume of data collected was staggering, but machine learning models successfully cataloged over 127,000 distinct crow calls. The AI identified unique vocal signatures that varied depending on the age of the bird and the specific individuals they were interacting with. This exposes a system of social cryptography. The crows use complex vocal arrangements to track relationships within their flock, actively adjusting calls based on their memory of past interactions and alliances. But as these AI models become highly tuned to the rich dialects and cultural exchanges of these species, yet the microphones are also capturing something else. They are picking up the mechanical tear of habitat destruction. The habitats that support these complex communication networks are under immediate physical threat. Illegal logging and poaching operations continue to aggressively push into protected zones, leaving charred clearings behind. The exact same machine learning models developed to decipher animal linguistics are now being retrained on a different dataset. They are learning to recognize the acoustic signatures of chainsaws, logging vehicles, and gunshots. This intelligence is deployed directly into the field through Rainforest Connection's Guardian platforms. Built to withstand harsh tropical conditions, these solar-powered acoustic monitors are mounted high in the canopy to listen to the surrounding miles of forest. They rely on edge computing. Instead of struggling to transmit massive, raw audio files over weak cellular networks, the Guardian devices run the deep neural networks on their own internal hardware, processing the soundscapes locally and autonomously. The moment the onboard AI detects the pattern of a threat, it triggers an alert. The device sends the exact GPS coordinates via satellite directly to mobile applications used by rangers on the ground. This is a critical operational upgrade. Moving from delayed post-incident data processing to instantaneous edge inference transforms passive observation into an active, life-saving intervention. The scope of this technology is expanding far beyond isolated parks. Initiatives like Project Guacamaya are networking thousands of these autonomous sensors into continuous grids spanning dozens of countries. This software interface demonstrates how these platforms monitor baseline ecological health. By tracking hundreds of distinct species simultaneously, the system provides an empirical, minute-by-minute measurement of biodiversity levels and habitat recovery. Connected together, these localized nodes form an automated acoustic shield. It functions as an early warning immune system for the planet, constantly listening for localized infections of illegal extraction. Artificial intelligence has given us the tools to prove that the non-human world possesses undeniable syntax, culture, and social intelligence. Having confirmed that these ecosystems are alive with complex communication, humanity now bears the profound responsibility of ensuring those voices are protected from silence.